asked chirality, it's handedness, the fact that you have the same fingers in your hands, but they don't match. You cannot put them together. Like left hand and right hand are different, right? Same way, there are molecules that are right-handed and left-handed, and all amino acids are left-handed, and all sugars are right-handed. That is a mystery of life, origins of life, and very recently a Bill Kent graduate probably solved that mystery. Yes, which was a combination of, yes.
More than Bill Kent graduate, it is like Harvard PhD student.
Yes, exactly, but let's not forget that he's also a Bill Kent graduate, yes.
Because not every Bill Kent graduate is at the same level.
Exactly. Yeah, good. So that's what handedness is. Now let's find. So that's how this and this is different, right? One is right-handed, screwing in, screwing out. Okay. Now let's find the magnetic field in this system. Okay. So I will just. I'm tempted to draw this again, but let me not draw it again, but just duplicate it and make it bigger. Okay. So what did we realize here? We realized that the magnetic field outside would be 0 and magnetic field inside would be something, right? Let's concentrate on just one of them. So for only one of them, there will be a magnetic field pretty much straight over here and straight over here, right? And we can imagine an ampere loop like this. Okay. So let's say this loop has a length of L. The loop has a length L. So what is B dot dl here? The B dot dl integral.
2 times BL.
2 times B times L. Does everyone agree with this? Because as I'm going this direction, it's B times L. Then I assume that the magnetic field is in this direction, so it's perpendicular to this one. Then it's B times another B times L over here, so 2BL, right? 2BL must be equal to mu 0 times n times I, and n is the number of currents coming out in here. Number of currents enclosed. Very good question. So let me just write another step. This has to be mu 0 I enclosed. Do you agree with that?
Yes.
Then I enclosed is n times I. Do you agree? Where n is number of currents enclosed. So mu 0 n times I. As a result, we get this. B is equal to mu 0 times let me just put 1/2 in front. It's 1/2 mu 0 times n over L times I. Okay? Or 1/2 mu 0 Ni, where n is n over L. So n over L is the number of turns per unit length. What do you notice about this? Is that it doesn't depend on distance. Do you notice that? Doesn't depend on this distance, right? But of course, we have assumed that that distance is very, very small with respect to this distance. And we hence ignored many, many things here. Fringing effects, like there will be magnetic field feels like this, but it will actually have some turns here, right? But we are ignoring them. So since it doesn't depend on distance, that gives us yet another reason to think that magnetic field due to this one will create a similar amount of magnetic field over here, which will cancel this one out. Okay? So as a result, you will have a situation. Can I paste? No, I can't paste. Let me just copy this one more time. Paste it here. So what this formula that we have discovered is telling us is that, let me just erase everything here and make this bigger. So it is telling me that this one will create a magnetic field in this direction, which will be 1/2 mu 0 Ni. Do you agree with that? Also, in here it is 1/2 mu 0 Ni, while the bottom one will create in this direction 1/2 mu 0 Ni, and in this direction 1/2 mu 0 Ni. But also over here 1/2 mu 0 Ni, and also the same with this one, but in the opposite direction. So these ones will cancel each other out. B is 0, B is 0, but over here B is mu 0 Ni. Okay? So for a solenoid, we have discovered that if you have a solenoid, let me just draw a solenoid. Solenoid'in Türkçesi solenoid. What? Yes, as far as I know. And it tells us that the magnetic field inside the solenoid will be mu 0 Ni, where N is turns per length. Okay? This is what we got from this investigation. Yes?
We said that for the capital N, we said number of currents going in. Is it is it correct to say that because current is something continuous?
Yes.
I know, so you cannot count it, like it should be.
Yes. This is wires, literal wires coming out. Like there's one wire, one eye, second wire, second eye, third wire, 3i, 4i, 5i, like that. And I'm drawing a So you have a certain amperes loop, right? And inside that amperes loop, there are a certain number of currents coming out. So mu 0 times n times I is B dot dl integral. Okay?
It's not an approximation.
It's not an approximation. Do you mean like it's not continuous? That's the problem?
Yeah.
Okay. Now I understand your question better. We are assuming here that number of turns are so many that it's okay, or you may be counting like maybe you are counting not all of the currents. Let me make it so that it's definitely not. So maybe it's 5.5 currents. Fine. You will still get 5.5 divided by unit length. So everything will be fine. You have a question? Yes.
How many turns does the solenoid require in practice to match with our calculations?
I don't know. But the more the better. You have to have longer solenoid. Ideally, it has to be longer, and the wire has to be as thin as possible so that the geometry of the wire doesn't get into this kind of stuff. But don't worry about this stuff. You usually just calibrate everything anyways. Okay. Okay. Nobody knows what happened, but example. You can think of a toroid as well. This is actually, let's not look at it as an example, but let's talk about toroid as well. Toroid is the thing, is when you have a solenoid wrapped into a circle like this. So let me just make it larger. Okay. So it has an inner radius. Can I draw it again? It's very bad. So let me first draw the inner radius A and outer radius B. Right? And then I will put a toroid in between. I'm drawing it like this, but imagine that it's very, very tightly wrapped. Okay? So it has an inner radius A, outer radius B, and the question is, what is the magnetic field at a distance in between A and B? So I have some R here in between. What is the magnetic field at that point? Do you understand the question?
Ampere's law.
So you apply Ampere's law here. Of course, you do know which way the magnetic field is going, right?
We don't know the currents.
Okay. Even if you do know the current, it's very hard to imagine. So I have to give you the direction. Inside it goes in, okay, and outside it goes out. So if that is the case, then which way is the magnetic field? Just tell me if it's clockwise or anti-clockwise. Clockwise, right? It goes like this. Right? So integral b dot dl would give you what?
B at that r times 2 pi r.
B at a certain range r times 2 pi r, and it has to be equal to mu 0 times I enclosed, right?
Which is n times I.
Exactly. So it's mu 0 times n times I. So for a toroid, the magnetic field inside the toroid changes from A to B. It changes like this. Mu 0 n I over 2 pi r. All right? What happens outside this toroid?
It should be 0 because
Outside it is 0. Because if I draw outside, okay, let me use another color for that one. Barbie color, right?
Ya siz yapmayın.
Why not? What is I enclosed for this?
I enclose this 0.
I enclosed is 0 because
I minus n.
for every I going in, there is I going out. So the magnetic field is 0 outside and inside as well. Inside as well.
Why?
Enclosed current is 0. There is no current going in or out. Okay? So next up is a subject that finishes this chapter, but a subject that we never ask in the exams, I guess.
Her şey paramagnetism vesaire.
It's Bohr magneton.
Magnetism.
Okay? So what should we do? We should do it, right? Okay.
Çok havalı ama.
Don't you always want to learn science for its own sake? So this will be like 25 minutes of that. Okay? So I will talk about Bohr magneton, but it will be hopefully fun. You remember our problem with electron falling on top of the atom, right? So Bohr had a great intuition, and for some mathematical reasons, for some experimental reasons, he just said that angular momentum is quantized. Okay. A little bit of story. Story time? It all starts with something called black body radiation. Okay, black body radiation. Black body radiation looks like this. This is experiment. So let me just give you some backstory. Black body radiation, for example, is basically, okay, this is frequency and this is energy density. So energy density per unit frequency. So how much energy do we get from the sun? Let's say I get it from the sun. Okay, for example, the energy between this much frequency and this much frequency compared with the energy between this much frequency and this much frequency. This is what experiments would show. Okay? This is what theory would show. It was called ultraviolet catastrophe. When you go to ultraviolets, actually all energy should be there, but it is not. Somehow those frequencies don't get excited. So far, did you follow? Yes? Big problem in classical physics. Then 1900s, Planck says something really, really crazy. Absolutely crazy. So crazy that even though it fits perfectly to experiment, he himself doesn't accept it. Okay? What is that crazy thing? He says that, you remember harmonic oscillators? He says that harmonic oscillator cannot have any energy it wants. Classically it can, right? Can it be zero energy? Yes, it can. You just leave it like that, it's zero energy. You put one joules of energy, okay, 2 joules, 2.172, doesn't matter, right? But what Planck said is that if you accept for a moment the crazy idea that not all energies are accepted, then you get this curve. Planck tells us that in 1900s that harmonic oscillators only can have this energy, where this is a number, just 1, 2, 3. This is Planck's constant. Planck's constant. And this is frequency. That's another crazy idea. It also tells us that classically, can I put 1 joules, 1.1 joules? What it has to do with its frequency? Nothing, right? Are you getting it? Like I can push it as much as I want. It doesn't matter how stiff the spring is. I can put small energy, large energy. But Planck says that no, when you have stiff bonds, then they accept only large amounts of energies. Okay? When the natural frequency of the oscillator is high, you can excite it, you can give it enough energy only if it accepts it. So that's how it resolves. So basically what happens is that normally, classically, these high frequency oscillators would get all the energy in the world, but Planck says that if we accept this is the case, then they just don't accept that energy, so they stay poor. Yes?
What do we mean by accepting?
Good question. We mean this. Let's say I give you, is it okay that we are doing this and you will not be asked in the exam about this? It's just physics. So I give you money. We like money, right? But you are sharing it with everyone, right? I give all the money to you, but you keep sharing and you keep sharing it with each other. That's what happens with gas molecules. They have energies and they share it with each other, right? And that also happens with the lights inside the sun. They share their energies with each other, okay? And they get normally since there are much more light particles that have higher frequency inside the sun, okay, they get lots and lots of the energy. Okay, did you follow this? Yes. When were you born? When were you born?
I was born in 2003.
2003. Everyone 2003?
No, 2000.
Most of you 2002? What?
2000.
2000. So most of you, let's say 2000. So if we look at like how much energy there is on 2003, 2001, 2000, it will obviously be 2000 because there are just so many of you. Do you see? But let's say people who have birth dates of 2000 don't accept money unless it is 200 liras. Do you see? So you keep giving each other 10 liras, 50 liras, but they just can't get it because there's never enough of 200s that you can accept. That's what it means. Okay?
Quantized means n is taking integers only.
Yes, exactly. So oscillators only accept HF, 2HF, 3HF, etc.
But in this case, if we increase f, E is going to increase.
If we increase F,
E is going to increase.
Mhm.
So we expect still that.
no. This is energy. That's right. But if you do the mathematics of it, since imagine this, there's never gas atom that gets enough energy to share it. So you ask for very lot of energy. Otherwise, you don't accept any energy. But that energy never comes together. It's exponentially less probable for energy to come together and excite.
So in this graph, what is the U over this? Is it
This is
different
energy
from
density
that?
per unit frequency. Okay? So far so good. So Planck has this crazy idea that oscillators only get discrete amount of energies. 10 years later, okay, let's not go 10 years later. 1905, Einstein uses this idea to describe photoelectric effect. What is photoelectric effect? Are you okay? Still? Yes?
John, before that, may I ask something? What is the real life graph? The blue one?
The blue one is the real life graph, and the green one is the theory fitting perfectly to experiment once you accept this weirdness. Then there comes this experiment where they shine light, okay? But normally, as in the oscillators, we don't attribute frequency to energy of light. That's nowadays we do that, but back in the time, it's just an oscillator. It's just an electromagnetic wave, right? Light is an electromagnetic wave, can have any frequency, and its energy has nothing to do with its frequency. It's wrong now, but 1905 was okay. Okay? So, what we would expect, let's say you have a metal. Metal has electrons. You want to kick out some of the electrons. You need some energy. What do? You supply that energy with light. But it turns out that you might try, for certain metal, you might try putting a lot of red light and nothing happens. Lot of red light and nothing happens. But a little bit of blue light and electrons start going out. Okay? How do you explain this? So, red light has frequency F1, blue light has frequency F2. F2 is larger than F1. Okay? And Einstein tells us that also light has this energy packages. Okay? So no matter how many of these packages you send, HF1, it's just not enough to excite the electron to kick it out. You can send thousands of them and you would have total of 1000 HF1 sent into the system, nothing happens, right? But you send 10 HF2s and you kick out 10 electrons. Do you see?
Can I ask something?
Yes.
Those 1000 red lights, won't they excite the system
Thermally, yes.
You could melt.
Yes, you could even melt, maybe,
Perhaps evaporate.
but you cannot kick out electrons. You have to have just the right amount of energy. So far, so good. So this worked like a charm. Like it was yet another experiment that was described by discreteness, right? And now we are in 1910. They have these atoms and atomic spectra, and they follow some rules. Okay, they see that, for example, they look at the universe. The universe is composed of hydrogen gas, and they just see these lines, like let's say this is minus 13.6 electron volt. This is 13.6 over 4, and this is minus 13.6 over 9. Curiously, you have discrete energies, like you have this energy present in the experiments, this energy present in the experiments, and this energy present in the experiments, for some reason, right? So Bohr starts with this quantization. Since we started quantizing stuff, let's quantize angular momentum. And he says that, yes?
If it's not the real reason, if it's not related about the frequency, what is it related about now?
Now it is related to frequency. Nowadays, everyone in science community accepts that energy of light is transferred in packages, and those packages have energies of h times f.
Yeah, I understand the opposite.
Yes. So this discreteness, Bohr takes it all the way to atoms. Okay? Was it helpful or waste of time? No? Good. Then let's continue. So Bohr tells us that for everything to fit experiment, we just have to accept that angular momentum of an electron is quantized, and it's n times h bar, where h bar is h over 2 pi. Okay? This is Bohr's model. That's it. The rest is classical physics. He just says that electron cannot just go this way, has to stay in orbits which are discretized like this. Why, Bohr? Because that is what is going to fit to experiments. So how do we fit it to experiments? We have to remember electron going around. So this is my electron, this is my proton, right? This is hydrogen atom. What is the angular momentum? M times V times R. Do you agree with this? Yes? So what is the energy of this system? Let's do it all the way. What is force? K E squared over R. Do you agree with that? Must be equal to mv squared over R.
Why is it only R?
Squared.
It's also equal to the interactions.
Okay. This is correct, right? How about energy? The energy of this system is mv squared over 2 minus ke squared over r. Do you agree? Did you follow this?
Yes.
So, what do I get? Have you done this in high school?
Probably yes.
Okay, good. Ke squared, then maybe it's pointless doing it again. Anyways, so energy is what? mv squared over 2, which is ke squared over r minus ke squared over r. So energy is minus ke squared over 2r. So far so good? Do you have any problem here? No? Let me also write down Bohr's condition. Bohr's condition is that MVR must be n times h bar. Right? So what can I derive from this? I can derive V. Do you see it? Let me divide this by this. And what do I get? V is ke squared over nh bar. If I'm wrong, please correct me. What is R? R is nh bar over mv, which is nh bar over m times ke squared n squared h bar squared. Let me put r back in. E is equal to minus ke squared over 2 times. Are you following? 2r, and in terms of r, I have n squared h bar squared and ke squared here. So what do I get? E is equal to minus k squared e to the 4 over 2 h bar squared times 1 over n squared. Okay, and with this, yes?
M kayboldu. Bana böyle.
N
M. What happened to the
n is here.
M?
M is M has disappeared. Let's put M back. Where is M? At the top, right? There it is. Are you with me still? Surprise, surprise. This is minus 13.6 electron volts. Okay? Yes? Are you happy?
This is not true today.
This is true today.
But it says we have orbits, electrons of orbits.
Yes?
Is it true?
Very good question. So it is, no, it's no longer true in that sense, because, okay, 4 more minutes, right? I haven't arrived at Bohr magneton yet. It's just Bohr atom. Let me tell this. So what happens is that so imagine you have this, but for 15 years you don't see the following. For 15 years you don't see that this thing was very much showing your ear like this, even more acrobatic stuff, because it's simply this. If you assume that this is a wave, so you have to wait 15 years for the Bohr to come out and say that, guys, do you remember light was a particle? Yes, we remember. Do you remember it was also, no, sorry. Do you remember light was a wave? Yes, we remember. Do you remember Einstein said that light is also a particle? Yes, we remember. Do you remember that electron is a particle? Yes, we remember.
Then why cannot it be?
Why can electron be also a wave? So that's crazy, but like it takes 15 years to come up with that and say that matter is also a wave. So if you do that, you just simply put a wave here, and that wave has to come back to itself. And that's the de Broglie condition, okay? And you basically get Bohr's condition from de Broglie condition. All right? What happens 1 year later? Schrödinger's equation. That explains everything. So it's an equation that describes matter waves or wave matters.
So photon has a mass. Photons have a mass.
No, that's a
But electron
electron has a mass, and it has a Schrödinger's equation. There's an equation for photon as well. There's a Schrödinger equation for photon.
so it has a mass or not?
No, in that equation there's no mass, but you can it's a relativistic equation. It's actually not a Schrödinger. Okay, it's too advanced for us to discuss right now. But
15 years later.
no. That it's not about the science not being there. What was Bohr magneton? Do I have time? I have 1 minute. Let me finish up with the Bohr magneton next time. Do you have any questions on this subject? Yes.
I was about to ask that. This only is applicable for one electron system.
Yes. And it's no longer applicable. So right now we have, it's a nice story that led us to Schrödinger's equation, and Schrödinger's equation explains all this, accounts for all this, and then some. Okay?
So aren't they parameters because we can only have 1, 2, 3 electrons, but we can't have 1.5 electrons? Is it because of that?
Say it
Or
again?
Is it something else?
Is it because, what?
Is it because of we can't have 1.2 electrons? We can have 1 or 2 electrons, or is it something else?
Do you mean Pauli exclusion principle?
Yani bu diskretlik elektronların diskret olmasından mı geliyor? Sebebi başka bir şey.
No, the discreteness comes from confinement of electrons in an atom. So if you have a free electron going anywhere it wants to go, then you would have continuous energies. But if you put electron in a box, an atom is a box for electron, then you would get discrete energies. And because the electron has to fit to the boundaries, it's like a wave, and when you put a wave inside a box, it has to fit to the edges, right? So you will have this harmonic series, like F frequency, then 2F, then 3F, right? It has to fit the box. That's where this discreteness comes from, confinement. Thank you. Let's have a break.